when I put a data set, the points from a cloud, and this cloud has some parameters like its center, its size, its orientation. It's like just the shape of the cloud, right? And to describe this shape, we need firstly to understand the location of the cloud. And imagine that you have two data set with two features and millions rows of the data. And on coordinate system, it looks like that, where all the points are spread out across the whole coordinate system. And if I ask you what are the coordinates of this cloud, you probably won't answer, because the cloud itself has no coordinates. We just don't know which point to select to represent the cloud, right? And to find this point, we just need to find the center of mass. So that's called mean, and it's just literally the center of mass of the cloud. And the mean is noted as mu, like that, and it's calculated individually for each feature. So if you have a data set like x1 and x2 with 3 observations, 1, 2, 3, and 2, 4, 6, and if you want to calculate the mean of this data set, you need to calculate the mean of first term, x1, and the formula looks like that. We just need to sum up all the observations for specific feature and divide it by the number of observations. So for first feature, we just write like 1 plus 2 plus 3 and divided by the number of observations 3, and it is equal to 6 by 3, so it's equal to 2, right? And we do the same for second feature, so mu x2 is equal to 2 plus 4 plus 6 divided by 3. So it's equal to 12 divided by 3, it's equal to 4. Okay, and so the center of this cloud, of this data set, is the vector of 2 and 4, right? But why do we need to know the center? So imagine that we have two clouds. Cloud A has 3 points with coordinates 1, 2, and 3 correspondingly, and cloud B with 3 points 1001, 1002, and 1003. And if I ask you to compare them, it may seem that cloud B is much bigger because it's located in thousands, and so it's just way further than cloud A. But they are actually identical. So all the points are 1 unit apart from previous point. Okay, and so they just have different location, but the shape is identical. And you can imagine that you have like Google Map with, and you are looking at 3 identical buildings on different streets. I don't know, like that, right? And they are on the same distance from each other, but just in different streets or just in different countries even. Yeah. But the shape of the streets is identical, right? And to understand this better, to be able to compare them better, we need to center the data. And centering the data means that we just need to subtract the mean of the data from each point. And it shifts all the cloud to the center of coordinate system. So the center of the cloud is shifted to the center of coordinate system, and that means that the mean of each feature is equal to 0 after that. Okay, and we do centering not only just to understand this better, but because we are usually more interested in hidden patterns within the data, like inside the cloud, but not the location of the cloud. And a lot of statistical measurements, I will show you later, works with center data. Okay. Well, and after that, we can work with find the size of the cloud, like it's how the cloud is spread. So to do that, we need to calculate the variance, and the variance formula looks like that. We do it as well independently for each feature, and we just take an average of squared distance of that feature from its mean. So like that minus mu squared. Okay, and okay, imagine we let us plot some points like that, right? And their mean. Let it be -1, -3, 1, and 3. Okay. And so when we subtract the mean from the point, we just calculate the distance from the point to the center of the cloud, right? So when we do that, we can get like distance 1, distance 2, distance 3, and distance 4. Okay, and actually this inner part looks exactly like centering, and that's true. We just it's the same if we just move the cloud to the center, and without this term, with this term equal to 0, just sum up the distance from the 0 to each term, okay, to each point. But why do we need this square term? So if you calculate the distance 1 and distance 2, you can see that the distance 1 is negative, it's -1, but the distance 2 is positive, distance 2 is equal to 1, right? So when you sum them up, they cancel each out, so it's going to be equal to 0. And when you do that for these 4 points, we have -3, -1, +1, +3, so it's equal to 0. And in that case, variance is going to be equal to 0, and that means that the cloud has like no shape, it's not spread out in the space, but you can see that that's false. So to deal with that, to remove this cancellation, we need to square each term, each distance. And not only that, we do squaring because imagine you have like center cloud over here, and a lot of points with distance equal to 1 nearby the center. And when we calculate the variance for that case, it's going to be very close to 1, right? But if we suddenly get some outlier over here, and this outlier, so the shape of the cloud looks much bigger, right, with this outlier. But if you have a lot of points near to the center, they're gonna reduce the impact of this outlier. So imagine that we have 1 plus 1 plus 1 100 times, and after that plus 16, right? And we divide it by 100. So the variance is gonna be smaller because we have a lot of small terms plus 1 big term and divided by huge number, so it's gonna be small. But when we do squaring, we understand that when the point is 1 unit apart from the center, it only brings 1 squared to the variance, it only brings 1. But when the point is 4 units apart from the center, it brings 16 to the variance. So with squaring, we are sensitive to the outliers and we pay attention to them, right? Okay, and one important thing to know about variance is that we have something called population and something called sample. And sample, imagine that you are measuring something in your university, and people in your university's population, it can be, for example, 1,000 people, right? But you measured 100 people. And if you're gonna calculate the variance for your measurements, the mean is calculated for this 100, and it's not fully representable, right? Because if you measure the whole population, the mean can be very different, right? Because the whole population could have some outliers, and so the mean can be different, and the variance will be probably will be very different in any direction. And to deal with that, so it's like equal to that we do some statistic for subset of future full set, right, of something. And to do that, we need to introduce something called Bessel's correction. And the idea is that in this variance form, instead of dividing the sum on just number of observations, we divide it by the number of observations minus 1, right? So it's going to increase the variance, and it's probably should become much closer to the real variance. Okay, hope it makes some sense. So after that, we can move forward from variance to covariance. So variance describes the spread of each feature independently, but variance cannot tell us how the features are related, and that's why we need something called covariance. And covariance just measures how the features move together around their means. So to calculate covariance, we just need for each observation, so it's summation, take the deviation of x from its mean and multiply it by the deviation of y from its mean. Okay, and after that we need to average these products. And that's our covariance of two features x and y, right? So covariance is calculated over the whole data set. And the final covariance is just a one value, which is a global summary of how two features move together. So imagine it's like for each point, we calculate the contribution. So when the deviation of the first term is positive and of the second term is positive, the product is positive as well. So it means that covariance has positive, is positive, right? When this is negative and negative, it produces positive. And when it's positive or negative and negative, or negative and positive, it gives us negative. So if x and y deviate from their means in the same direction, their contribution to covariance is positive. And if they deviate in opposite direction, their contribution is negative. And covariance is just the average of all these contributions over the data set. So let's build some plot like that, where the center is our mean. And we have points, data points like that. So we know that we can see clearly that for each point independently, the deviation is negative, right? And for x and same for y axis, they are negative. And when we sum up all these deviations and multiply negative x deviations and negative y deviation, we have positive covariance effect, right? And that means that that our data is increasing, like our cloud is tilted up, right, for this part. And then we also have the second part where we can see that deviations are positive for x-axis, right, and positive for y-axis. And when we calculate the product and sum it up, we can see that there are also positive terms. So when we sum up all the deviations, the covariance is positive, right? So the cloud of these points is tilted up, as you can see, right? So on these plots, on the first plot, you can see the same diagram I've shown you right now, with positive covariance, where the cloud is tilted up, right? And on the second plot, you can see some example of negative covariance, because the x deviations are negative, but the y deviations are positive for the left part, right? And that's why we have negative impact on our covariance. And on the second part, we can see negative y deviations and positive x deviations. So when we sum up all this together, we can see some negative covariance value, okay? And covariance can be, so as I said, covariance show only like a tendency to grow or to decay. So it can show only linear relationship. It cannot answer like it first increased first 2 seconds and after that it decreased. And that's why it only can handle some linear relationships. And if you have some parabolic function, you know that, for example, for these 2 points, we have this negative deviation of x and this positive deviation of x multiplied by the same deviation of y. So in the result, when we sum this up, the covariance is going to be equal to 0. And that means that there is no linear relationship, but it doesn't mean that there is no relationship at all, because on this example, we clearly know that there is some quadratic relationship, right? And here on the third plot, you can see that there is no relationship again, because just terms cancel each other out. And as I said, covariance returns one value. This value called magnitude. But we cannot clearly interpret it, because this value depends on the scale and units of the features. And just if I tell you covariance is equal to 100, what does it mean? Is it large or small? But we know that if the cloud is more spread out along a diagonal direction, this covariance becomes larger in absolute value. And if the points are closer together, covariance is smaller. So on this plot, you can see that On the left part, you can see static covariance value equal to 10, and all the plot points are closer together, they are tied. And on the right, you can see how the covariance value magnitude is changed when we grow the distance among the points, so it's spread out our cloud, right? Fine. So variance describes spread along individual axes. Covariance describes the tilt between pairs of axes. But now we can put all this information into one object called covariance matrix. And for two features, the covariance matrix looks like that. So C is equal to a matrix of variance of x and covariance of x and y, and covariance of x and y and variance of y. These two terms elements are same because covariance of x and y is the same as covariance of y and x. Okay. So why do we need this matrix representation? The reason is that the variance tells the split along the original feature axis, so just for one feature, right? And just for x-axis and the y-axis, for example, right? But covariance tells where the cloud is tilted, right? And sometimes we want to ask a more general question like how much does the cloud spread in any direction, not only along the original axis, like that, right? So we can have some example when the cloud is not mostly spread horizontally or vertically. Maybe the cloud is spread along a diagonal direction, right? And to measure that, we need the covariance matrix. And to understand how it works, I will introduce you some eigenvectors and eigenvalues. And as we discussed before, a matrix can be understood as a linear transformation. And when we multiply a vector by a matrix, the matrix can change the vector in two ways. It can change its length and it can change its direction, right? So if we have some vector and we multiply it by some matrix, it can be increased. It can be increased and change the direction, or just change the direction, right? It's like imagine you have vector 1, 1, 1, and you multiply it by the vector 1, 3. So the one coordinate is the same, but like that, the orientation is changed, the direction is changed, right? And for most vectors, both things happen, and the vector gets stretched or compressed, as I show you, and it's also rotated into a different direction. But there are some special vectors which do not change direction after the matrix transformation, and they may become longer, shorter, or just flip the direction. But they still lie on the same line, so it can have like vector. And when you multiply this vector type of vectors on the matrix, it's only either stretched or compressed or just changes the direction. Okay, and these special vectors called eigenvectors, and formally we can write them like that: some matrix A multiplied by some eigenvector V is equal to some eigenvalue multiplied by eigenvector. So this equation means that multiplying the vector by the matrix gives the same vector direction, only scaled by this eigenvalue. So an eigenvector is just a direction that a matrix doesn't rotate. And the eigenvalue tell us how much the matrix stretches or compresses that direction. Like if this eigenvalue is equal to 3, this means that the matrix stretches the eigenvector by a factor of 3, so it's just 3 times bigger, right? But why does this matter for covariance matrix? So covariance matrix describes spread in terms of original terms, right? And imagine that we have some 2 dimensions, so 2 features, and the strongest direction of variance may not lie along one pure feature axis, but it can be in mixed direction. So when we're working with covariance or variance, we are looking only on 2 axes, per axis direction independently. But what if the strongest direction of variance, like of the spread, is on some diagonal? So it's just on some mixed vector. And this vector, let's write this vector as v is equal to a and b. And this direction defines a new mixed feature. Let's call it z is equal to this value a multiplied by x axis plus b multiplied by y axis. So it's some part of direction of x axis plus some part of direction of y axis, right? And so it means that we are not looking only at feature x or at feature y, but we are looking at new combined feature made from both of them, okay? And to answer the question, how much variance does our data have along this new direction, we need to derive some formula. So we're gonna calculate the variance of this new vector v, right, which is some combination of two vectors. So variance of this combination z is equal to average of squared deviation, right? When the data the data is already centered, so I don't do subtraction from the mean, okay? So let's substitute this z to the variance, right? And when we substitute that equation here, so it's going to be equal to average, and let us expand the square immediately. So it's going to be a squared by x squared plus 2 times a bxy plus b squared y squared. And now we can split the sum into separate terms. So variance of the z is going to be equal to a squared because it's constant, and average sum of x squared plus 2ab multiplied by average x by y, and plus b squared multiplied by average y squared. Right. So we can see that each of these sums can be identified as variances. So this part is actually a variance of x. This part is a variance of y. And this part is covariance of x and y, right? So we can rewrite this equation like that. It's a squared by variance of x plus 2ab covariance of x and y plus b squared variance of y. So this formula tells that the variance of the mixed feature depends on three things: the variance of x, the variance of y, and the covariance between them. And now we can write the exact same expression using the covariance matrix. So for two features, we know the covariance matrix looks like that, right? And now we can multiply the covariance matrix by our vector. So covariance multiplied by v is equal to variance of x, covariance of xy, covariance of xy, and variance of x or y. And we multiply it by vector a and b, right? And I remind you that we multiply a row with a column, so it's going to be equal to a variance of x plus b covariance of xy, and in the second row it's going to be a covariance of xy plus b variance of y, right? And now we can multiply this result by transpose vector v. So when we multiply this part on the transpose vector v on the left, we're gonna have a vector a b multiplied by this matrix, the same matrix. So we multiply a with a variance x plus b covariance xy, and plus b multiplied by a covariance xy plus b variance y, right? So when we expand this, it's going to be equal to a squared variance of x plus ab covariance of xy plus ba covariance of xy plus b squared variance of y. And when we sum up all this term together, we have a squared variance of x, and sum up these parts together, so it's plus 2ab covariance of xy plus b squared variance of y. So this is exactly the same formula we derived for variance of z, and therefore we can say that variance of this mixed vector in the new direction is equal to transpose vector v multiplied by c multiplied by v, right? So the covariance matrix allows us to compute the variance of any linear combination of features. Well, and now suppose that this vector v is eigenvector of the covariance matrix. So that means that when we multiply this vector by the matrix, we're gonna just scratch or compress the vector, but it doesn't change the rotation, right? And we already know that the variance along direction v is equal to this part, so we can substitute in this part vt multiplied by c multiplied by v, the cv part. So it's equal to transpose vector v multiplied by eigenvalue multiplied by v, right? And if this vector v is unit vector, meaning it has the line of 1, so it only represents the direction, then this part is equal to this part is equal to 1, so we have something like that vt multiplied by c multiplied by v is equal to eigenvalue. And this means that for a unit eigenvector of a covariance matrix, the eigenvalue is exactly the variance of the data along that direction. So to summarize, if we want to calculate the variance of the data in any direction, we can take a unit vector that represents that direction and compute this term with covariance matrix. And this gives us one number, which is variance along that direction. And it's going to be used in the next steps because some methods ask like which directions, which unit vectors give us the largest possible variance. And that's why all this stuff used, okay? So thank you for watching. Please comment the video for me to better understand how to improve my explanations.